Okay, hi, I'm Nick, and the topic of my presentation is sum of squares. The first thing we have to ask and answer is what is sum of squares? And definitionally, it represents the sum of the square differences from the mean, and it is also known as total variance. You can see here we have two different iterations of this formula. One lends itself to easier hand math, and the other one is more of a theoretical version, but one and the same nonetheless. Okay. As you can see in both instances, as highlighted in red, okay, the sum of squares is the numerator of the variance equation. And the variance equation, as we know, is the variability about the mean, which also happens to be the same definition of standard deviation. They're just represented slightly different. But first, let's zoom back out and see how does this fit into the larger picture. Okay, so if we start with sum of squares, we can then derive variance from that. And then from variance, we can derive standard deviation. Okay, so variance and standard deviation can be thought of as being downstream to sum of squares. In other words, they are derivations of it. But let's ask another question. How do we get sum of squares to begin with? Well, the short answer is data. Okay, specifically, data collected as part of the process of answering a particular research question, which is part and parcel of the scientific method. But to put this in context, let's take a look at an example from the field of sport and exercise physiology. Okay, here's a relatively simple research question. What is the mean and standard deviation VO2 max, or maximal oxygen uptake, for 15 members of the Springfield College's men's basketball team? Over here to the right, we have data from subjects 1 through 15. In column B, we have each subject's VO2 max as represented by Y, with the sum and the mean at the bottom. In column C, we have each score, or Y minus the mean. And then in column D, we have Y minus the mean squared. Okay, so the mean, of course, at the bottom of column B is 51.13. The units here are milliliters per kilogram per minute. And then to get sum of squares, again, here is the formula that we addressed previously. We need to sum all of the values here in column D. And that 3,599 and change, that is our sum of squares. Okay, now to derive variance, we simply divide by the degrees of freedom, which is n minus 1, which would be 14, to get this 257.12 value. And then finally, standard deviation, we simply take the square root of that to arrive at 16.03 milliliters per kilogram per minute. So the mean is 51.13, and then the standard deviation is 16.03. Standard deviation, of course, is in units of the variable, so milliliters per kilogram per minute. Connections to research and statistics. Sum of squares, as we mentioned, is the cornerstone on which both variance and standard deviation are built. But beyond its role in descriptive statistics, the theoretical concept of sum of squares also appears in other inferential statistical computations, such as ANOVA, which is analysis of variance. Okay. As we've learned before, ANOVA is broken down into 3 different calculations. ANOVA measures and tests for mean differences among 3+ samples, and it involves separating the dependent variables' total variability into between group variability and within group variability. These are represented by the sum of squares for between and within, respectively. And then, of course, we have the sum of squares total. And it does this through a calculation of an F distribution, as we call it, which is a ratio of these 2 variables, between and within, but it uses the sum of squares. Okay, so final summary, sum of squares is the starting point for deriving both variance and standard deviation. Sum of squares is the numerator of the variance formula, and it is a fundamental concept to extrapolating both descriptive and inferential statistics. Thanks for watching.